Welcome back. In today's lecture, we will discuss conservation of mass equation. The basic principle of mass conservation states the mass of a system remains constant. This is a law that is available for a system, that is, of fixed material particles. As you know, that we like to use controlled volumes in fluids, so we will have to find a conversion of this law to control volumes. And for this, we use Reynolds transport theorem. We have a control volume CV and with a controlled surface. The mass can enter and cross the controlled surface. As we discussed in the last lecture, the Reynolds transport theorem says that the rate of production of the quantity, physical quantity that we are dealing with, plus the net diffusive flux out of the controlled volume across the controlled surface should equal the rate of change of physical quantity contained within the controlled volume, that is the local rate of change, or the rate of accumulation, plus the convective flux of the physical quantity across the controlled surface. When the property is mass, the rate of production of that quantity is obviously 0 if we rule out nuclear reactions. The diffusive flux in the case of mass is also 0, and the rate of change of physical quantity contained within the controlled volume, which is the local rate of accumulation, is del m by del t. And the last, the net convective flux of the physical quantity across the controlled surface is rho AV out minus rho AV in, the net efflux. This can be manipulated to give del m by del t, the rate of accumulation of mass within the controlled volume, is equal to the net efflux of mass across the controlled surface. This is the form of mass conservation equation that we use in fluid mechanics. Let us consider a steady flow in a channel where the mass is coming in at the left end and is leaving out at the right end. Clearly, in steady flow, there will be no accumulation of mass within the controlled volume. So, the net influx written here is 0. Rho AV in minus rho AV out is equal to 0. For constant density, when the density of the fluid does not change, the rho in is the same as rho out. So, AV in is equal to AV out. A is the area of the channel at the inlet, V is the velocity at the inlet, and similarly A out is the area of the channel at the outlet, and V out is the velocity at the outlet. The terms 1, 2 or 3-dimensional flow refers to the number of space variables required to describe the velocity profile. This conical shape represents the velocity profile in a pipe, where Vz, the velocity along the z-axis, is a function of r alone. We have discussed earlier that if the flow is laminar, this profile is parabolic. It varies like r square, where r is the radius measured from the center of the pipe. We need only one variable r to describe this profile. That's why this is called a one-dimensional profile. Similarly, if we have a channel made of two parallel plates, the velocity profile Vz is a function only of y, the distance from the central axis. This is also a one-dimensional profile. If the channel is not straight but curved, but it is thin, in the sense that the cross-sectional dimensions are small compared to the dimension that we measure along the axis, then we can write the velocity along the axis is a function only of s. This again can be considered to be a one-dimensional profile. If we have a slowly tapering channel, the velocity is no longer a function of only one variable, because the velocity near the walls also changes in the y direction. So this is not truly a one-dimensional flow, but if the boundary layer where the velocity varies is thin, then the flow can be treated as a quasi one-dimensional flow. Consider flow past a circular cylinder with a velocity v0. If we take a plane perpendicular to the axis of the cylinder and look at the flow in that plane, we would see the flow within the plane to be like this. This clearly is a function of two space variables, a vertical variable and a variable along the flow direction. This flow pattern is independent of the third dimension. That is, we could take the plane anywhere along the axis of the cylinder and we'll observe the same flow. So that's why velocity profile does not depend upon the third dimension. It's called a two-dimensional flow. In a circular pipe, and if the flow is laminar, the velocity profile is parabolic and is given as V is equal to V max into 1 minus r square by capital R square, where r is the distance measured from the axis in the radial direction and capital R is the radius of the tube. V max is the velocity at the center line of the tube where it is maximum. How is V max related to V average? To calculate V average, we need to find out what is the flow that is taking place across the whole section of the tube and divide that by the area of the tube, and that will give you the average velocity. The process is that we consider a ring of thickness dr at radius r. The velocity there is given by the formula given here, V max 1 minus r square by r square, and so we can set up integration. The volume flow rate is integral over r from 0 to capital R, Vz, the velocity at that location, which is V max into 1 minus r square by capital R square, into the area of this ring, 2 pi r dr. And this, when we integrate, comes out to be 1/2 pi r square V max after putting in the value of Vz given by the velocity profile and integrating. This is equated to V average times the area of the pipe, pi r square. And so clearly we get V max is equal to twice the V average. The average velocity is 1/2 of V max. Let's again do this problem with a turbulent velocity profile. One of the most commonly used turbulent velocity profile in a circular tube is the 1/7 power law. Vz at any radius r is Vmax times 1 minus r by capital R, the radius of the tube, raised to power 1/7. And we find V average in the same fashion. We take a ring of thickness dr at a radius r. We write the volume flow rate q dot as integral over 0 to r of Vz times the area of the ring, which is 2 pi r dr. And this is equated to V average times pi r square. And from this we get q dot as 0.82 pi r square V max, and then we get V max is equal to 1.22 V average. So V max in the laminar flow is twice the V average, but in turbulent flow it is 1.22 times V average. That's because the velocity profile is much flatter than the parabolic velocity profile of laminar flows and extends very close to the walls of the tube. Let's do an example of the use of the mass conservation equation that we obtained for a control volume in this. Consider a water storage tank fed by a pipe of diameter 10 centimeter and drained by a pipe of diameter 6 centimeter. The water enters at a uniform velocity of 3 meters per second and leaves at a velocity of 2 meters per second. Calculate the rate at which the water level in the tank rises if the tank diameter is 5 meters. This is not a steady flow example. So we take an appropriate control volume. The rate of accumulation of water in that control volume is equal to the net rate of influx of water into the control volume across the control surfaces. So we have to choose a control volume that is appropriate. As far as possible, the control surface of the control volume should lie adjacent to the rigid walls across which there is no flow, like the portions here, here, and here. Why? Because they are adjacent to rigid walls, and so there is no flow across these parts of the control surface. The control surface should preferably chosen to cross the inlet and the outlet ports normal to the flow velocity to save on computational effort. Because if the surface is normal, the flow rate is simply velocity times the area of the flow. So an appropriate control volume is something like this, shown by broken lines. This portion at 1, the control surface, is perpendicular to the velocity of water. And this portion at 2 is also perpendicular to the velocity of water. So, if we apply the mass balance equation, the first term is rate of accumulation of mass, which is the rate at which mass of water contained within the control volume changes. The mass of water within the control volume is rho W, the density of water, times the cross-sectional area A of the tank and the height h up to which the water is stored in the tank. This is expanded as rho W A tank into dH by dt. They plug in the value of rho W and A tank. I get 1.96 into 10 to the power 4 kilogram per meter into dH by dt. This is the rate of accumulation of water in the tank. This should be equal to the net influx of water into the tank across the control surfaces. There is an influx across 1 and there is an efflux across the surface marked 2. So the net efflux is the water crossing the surface at 1 minus the water crossing the surface at 2. At 1, the density into the area, 10 centimeter diameter pipe translates to 7.85 into 10 to the power minus 3 meter square into velocity, which is 3 meters per second, minus the efflux at 2, which is density times the area, 6 centimeter diameter, times the velocity, which is 2 meters per second there. So the net influx of mass is 17.89 kilogram per second. This is equated to the rate of accumulation to obtain dH by dt. We could work with alternate control volumes as well. Suppose we had chosen this control volume as shown. We are not worried about the second recommendation, which said that the control surface should preferably be normal to the velocities. At 1, the velocity is inclined at 45 degrees to this. This would complicate the calculation. The area would now increase to the area of the pipe divided by cosine 45 degrees. But when we find the flow, we will only the vertical component of velocity would contribute to flow across that area, and the vertical component of velocity would be v times cosine 45 degrees. So the product of the velocity and area would still be the same, VA. So we should get the same result. Another example of a control volume is a little bit more tricky. Here we take a control volume where the top surface is taken to coincide with the top surface of the water inside the tank. As more and more water accumulate in this tank, this part of the control surface would move. The control volume would expand. Can we apply the momentum equation to this control volume? Yes, we can apply. But we must realize that while calculating the influx and efflux, we must take the velocity of the fluid relative to the control surface. Here, the control surface is moving up at the rate dH by dt. And so, the average velocity of influx at that surface would be velocity of water plus dH by dt. The velocity at which the water is crossing into the control volume, the relative velocity. To state it again, the velocity of the fluid crossing the deforming part of the control surface must be measured relative to the deforming control surface. So, V1 is the velocity of the falling water at location 1. The velocity of the fluid entering the control volume in a reference frame attached to this part of the control surface is V1 plus dH by dt. And if we use this equation, we would again get back the same result. Let's take another example. In very old days, the long distance train used to pick up water for their use from a ditch which was running parallel to the rails. The water was scooped up. As the train moved to the left, the water was scooped up into the reservoir. In this example, we have shown that the scoop is picking up a 4 centimeter layer of water. What is the rate of accumulation of water inside the control volume? We choose a control volume like this. In this control volume, there is influx only at one point, only at one location, this location. If we take unit depth of the scoop, then the area of the inlet is 4 centimeter into a unit depth, 1 meter. This is the area of the scoop. And this area is normal to the velocity of water moving in. The relative velocity of water across the surface is the same as the velocity at which the train is moving forward. So, if we know the velocity, we know the influx of water. The density of water times the velocity of the train times this area, 4 centimeter into 1 meter per meter depth. There is no efflux from this control surface. So, rate of accumulation must be just this, the density of water times the velocity times the area of scooping. This is the control volume that we use. The speed of the train is 108 kmph. There is no exit of water. So, the water is continually being accumulated inside the tank, inside the control volume. All right. Let's now go to the differential form of the mass balance equation, the mass conservation equation. An equation that we can apply to every point of the flow field. For this purpose, we consider within a fluid a cubical fluid element or a cuboid fluid element or dimensions dx, dy and dz as shown. There is a velocity field with component Vx, Vy and Vz. The rate of accumulation of mass within this volume would be, the volume is fixed, volume is dx, dy into dz. So, the mass contained within this is rho times dx, dy, dz. The only way this mass within the control volume can change is if the density changes. And if del rho by del T is the rate of change of density within this control volume, then the rate of accumulation would clearly be del rho by del T into delta X, delta Y, delta Z per unit time. And this rate of accumulation should be equal to the net influx. Let's calculate the net influx. Let us consider the phase with a normal in the minus x direction, which is the phase there. And what is the rate at which the mass is crossing this control surface in time delta t across this phase is the density rho Vx times the area, which is dz into dy, and times delta t. Next, let us consider the opposite surface with the normal in plus x direction or distance delta x away. This is the velocity is such, if velocity is positive, then the mass is moving out of this surface. So this is an efflux. That's why we put a minus sign. And we use the Taylor's expansion to get this expression for the net efflux across this surface in times delta t. Similarly, we write for the surface with normal in the minus y direction, in the plus y direction, in the minus z direction, and in the plus z direction to get these 6 expressions for influx and outflux. The net influx is obtained by adding these 6 terms, so that the accumulation delta rho by del T into the volume times delta T is given by the remaining terms of the efflux, the negative sign for converting this into influx. And the volume delta x, delta y, delta z cancels, delta t cancels, and the resulting equation is delta rho by delta t plus delta by delta x or rho Vx plus del by del y of rho Vy plus del by del z of rho Vz. This is equal to 0. In vector form, we can write this as del rho by del t plus del dot rho V. This can be expanded into del dot rho times V plus rho del dot V. Or this rather dot would be here, del rho times V. But this term and this term, what are they? This reminds us of the total derivative formula, Euler acceleration formula that we derived in this last lecture. This is nothing but d rho by dt, the material rate of change of density. And this results in d rho by dt, the material rate of change density, plus rho times del dot V is equal to 0. This is the differential form of the mass balance equation. Clearly, if the fluid is incompressible, by d rho by dt, the material rate of change of density should be 0. And then we get a simple expression, del dot V is equal to 0, or del Vx by del x plus del Vy by del y plus del Vz by del z is equal to 0. Since quite a bit of fluid mechanics deals with incompressible flows, so this equation is the equation quite often used as the equation for mass balance in the differential analysis. This equation is also known as the continuity equation. This is applicable strictly for incompressible flows or where we can assume the flow to be nearly incompressible, quasi-incompressible flows. Let's give an example of how we can use this continuity equation. The tangential velocity component in two-dimensional incompressible flow is given by v theta is equal to k by r, with k as a constant. What could be the possible radial velocity component? Clearly, we are now dealing with cylindrical polar coordinates theta and r in two dimensions, incompressible flow. So we'll use the form of the equation del dot v in cylindrical polar coordinates, and in cylindrical polar coordinates del dot v is 1 by r del over del r of r Vr plus 1 over r del v theta by del theta. And since v theta is a function of r alone, not of theta, the second term is 0. That means RVR is independent of R. From this is 0. This means that RVR must be independent of R. It should not change with R. That is, RVR can be a function of theta and t only, not of R. This gives VR is equal to some constant f, or rather some function of theta and t divided by R. VR varies inversely as 1 over R. There could be dependence on theta and dependence on time. If we talk of steady flow, there will be no dependence on time, so there could be a dependence on theta. All kinds of solutions are possible for this. The simplest, of course, is when f theta by t is 0. If f theta by t is 0, then Vr is 0. There is no radial velocity. The fluid particles are going around in circular path with only v theta velocity, which also decreases as r increases. So the velocity near the origin is very large, and the velocity dies out as 1 over r as r increases. This is known as a free vortex in fluid mechanics. We will have occasion to use this free vortex extensively in later calculations. The flow behind an aircraft consists of two trailing free vortices. You can see in this picture the vortice is rotating, the flow is rotating, the velocity is very large at the center, is slowing out as r increases. Another solution is when f theta t instead of being 0 is a constant, let's say minus k, then Vr is minus k over r. So there is a r velocity which also decreases as r increases, but is negative, is directed inwards toward the origin. A bathtub vortex, a vortex that you see in a bathtub, or when you pull out the plug in a sink and the water goes around in circles and is sucked in is called a bathtub vortex. An example of bathtub vortex is a hurricane. Hurricane can be modeled as a bathtub vortex. The fluid is moving circularly and there is a component of velocity towards the center of the hurricane. Next, talk of another concept, the concept of stream function. A very important concept, a very useful concept. Let us study stream functions for only two-dimensional steady and incompressible flows, so that the equation of continuity del Vx by del x plus del Vy by del y is equal to 0 applies. Let S1, S2 and S3 be three streamlines. Streamlines do not intersect. Let us consider a small control volume within two streamlines S1 and X2. This surface coincides with the streamline S1. This surface coincides with the streamline S2. Surface 1 is normal to the velocity, and so is surface 2. As you know, a streamline is a line which is tangential to the velocity. So there is no component of velocity across these two surfaces. If the flow is steady and incompressible, there is no accumulation of mass within the control volume, and so the mass entering at 1 should be equal to the mass leaving at 2. Since the location of surface 1 and 2 are arbitrary, I could take the control volume anywhere between the two control volume. What conclusion can we draw? That the mass flowing within two streamlines is constant at all locations. So the mass flow rate here is the same as mass flow rate here, is the same as mass flow rate here. Everywhere we have the same mass flow rate. VA1 is equal to VA2, the density being constant. So the spacing between the streamline increases where the flow slows down and decreases where the flow speeds up. If area A1 is more than area A2, then V1 should be less than V2. This is illustrated very nicely by this example. Consider the creeping flow about a cylinder. A flow at very low velocities such that Reynolds number is much less than 1. This is a picture that we shown you earlier. The flow looks quite symmetric. There is no separation. If we mark a few streamlines, we see a central streamline going like this and another streamline go like this. The spacing between two streamlines here is less than the spacing there. So what does that mean? The velocity on the shoulder of the cylinder is less than the velocity upstream. The spacing here is the largest. So velocity here should be smallest. In fact, this point is the stagnation point where there is no velocity. If we draw the velocity profile at the shoulder, this is the velocity profile. Notice that even a substantial distance away from the surface, the velocity of flow is still less than the undisturbed velocity out here. We will talk about this later. On the other hand, consider the flow of the fluid which is non-viscous. There is no fluid which is completely non-viscous, but it is possible to simulate this flow in an apparatus called the Haley-Shaw apparatus, where the fluid behaves as if the Reynolds number is infinite. There is no boundary layer, there is no separation in this flow. Notice that in this case, the distance between two streamlines is much larger upstream than on the shoulder. What does this mean? This means the velocity on the shoulder is much larger than the velocity upstream. The velocity profile is like this. This is very close to the undisturbed velocity. So velocity at shoulder is much larger than the undisturbed velocity. Of course, in an actual flow, the velocity at the surface must be zero. So this velocity must have a very sharp reduction to zero velocity. This is what the boundary layer that we discussed earlier and which we will discuss later on in the course. Let's again consider the same picture. Three streamlines S1, S2, S3. The flow between S1 and S2 is moving towards the right as shown. Consider point A on S1 and points B and C on S2. Clearly the flow across AB must be same as flow across AC. So as before, the flow between two streamlines is constant. The two streamlines actually act like a conduit for flow. No flow crossing the streamlines. Now we can associate a function psi with streamlines such that d psi is psi S2 minus psi S1. Since if we associate a function psi with S1, then the value of psi with S2 would be d psi greater. Stream function psi is a function which takes constant value for a given streamline such that the difference of values of this function for two streamlines gives the flow rate per unit depth between them in two-dimensional flows. Let's look at this in further details. Consider point P at location xy on streamline S1. The value is psi. Let's draw a vertical and horizontal line from point P to the next streamline S2. The volume flow rate across this must be same as volume flow rate across this. And this volume flow rate must be d psi because the value of the stream function associated with S2 is psi plus d psi. So d psi is the volume that flows between the two. Clearly d psi is Vy into minus dx, and which is also equal to Vx into dy, because it's only Vy velocity component which will create a flow across the horizontal line segment, Vx being along the line segment itself, and Vx would be the only component that will create a flow across the vertical line segment. This can be manipulated to give del psi by del y is equal to Vx and del psi by del x is equal to minus Vy. We can obtain these equations by formal mathematics also. Differentiating psi into a constant gives you del psi is equal to del psi by del x dx plus del psi by del y dy is equal to 0, or del y by del x is equal to del psi by del x divided by del psi by del y from this equation along a streamline, because psi is constant. Now, but dy by dx along a streamline is nothing but Vy by Vx. So, minus del psi by del x can be treated as Vy and del psi by del y can be treated as Vx. Same as before. Notice an important use of stream function. We can replace the two variables Vx and Vy by a single variable psi for incompressible steady flows in two dimensions. That reduces the number of unknown variables by one. Two variables Vx and Vy can be replaced by psi. This gives an important advantage in calculating complex flows. In case of two-dimensional cylindrical polar coordinates, the velocity components in the r and theta directions are given by Vr is equal to del psi by r del theta, and V theta is equal to minus del psi by del r. Psi is the stream function. Let's do an example. A stream function is given as psi is equal to 3x squared minus y cube. Is the flow incompressible? How can you find out the flow is incompressible or not from a stream function? Yes, we can find out the velocity component from the stream function Vx and Vy. Once we know the velocity component Vx and Vy, we can test with the continuity equation whether they satisfy the continuity equation or not. Vx is equal to del psi by del y, and here it would be minus 3y square, and Vy is equal to minus del psi by del x, and this would be 6x. Incompressibility requires delta Vx by delta x plus delta Vy by delta y is equal to 0, and this is satisfied. And so the flow is incompressible. Delta Vx by delta x is 0, delta Vy by delta y is 0. So that the continuity equation is satisfied and the flow is incompressible. There is a very interesting property of streamlines and stream function. Let us consider the function psi is equal to xy. Psi is equal to constant, that is xy is equal to constant lines are plotted in this xy plane and the rectangular hyperbolas of this shape. Vx is del psi by del y, which is x, and Vy is minus del psi by del x, which is minus y. Now, we have stated that no flow crosses a streamline. So, if we replace the x-axis by a wall, then psi is equal to xy. represents the flow in a half plane above the wall, assuming the viscosity is not there, assuming that the no slip condition does not apply. This is a particular kind of flow which we will consider later, called the irrotational or the potential flows. So psi is equal to xy can be used to represent the flow towards a wall, the flow coming vertically downwards towards a wall. And then the flow would split into two portions. This would be a stagnation point. The velocity would decrease as we go down and would increase as we go away from the origin in the two directions. Not only this, we may replace the y axis also by a wall, so that this first quadrant is the only region where the flow takes place. Psi is equal to xy, the stream function, also represents flow in a corner. This is a flow that comes here and goes towards this in one corner, with these replaced by solid walls. So what is the stream function of this corner flow? Psi is equal to xy. Simple. And the velocities can be obtained at any x and y by these formulae. Not just this, there is one more possibility. That we replace this streamline by a wall and replace this streamline, another streamline, by a wall. Then psi xy represents flow through this channel as well. And the velocities at any point x and y within this channel of this specific shape would also be obtained by differentiating the stream function xy. Thank you very much.